Hello, welcome back to Essentials of Computer Architecture and Organization. We are working through this advanced topic section. Section. We talked about a couple different ways of improving performance through parallelisms and data pipelining. And now we're going to be talking about power and energy, two things that are vital. If you don't have those, you're not going to be able to do any type of computation. So power and energy constraints are now the driving force to all devices from servers to smartphones. You can be thinking of these two different domains. A smartphone, it has a battery, and so you're limited by whatever that battery can produce. Servers, how much can you actually draw from your power supply? And so those are the things that we're talking about. So let's talk about those concepts one at a time. For power, it's a rate at which energy is consumed. It's measured in watts, milliwatts, kilowatts, or megawatts. Those may be things that you've heard about. In terms of definitions, if you want to know about this, 1 watt is 1 joule per second. So it's energy per second. So it's an instantaneous value. So the power at time t is given by this equation, the voltage times the current. And so that's what the power is. Energy, it's a fundamental property of the universe. It's measured in joules. So this is not something in time, but it's reported in watts multiplied by time. So kilowatt hours, megawatt hours, something like that. So for a constant power utilization, the energy used from time zero to T0 to T1 is you integrate over time the amount of energy. So that's shown down here. So it's either, you can be thinking of it in terms of this per se, if there's a constant power or power consumption, if it varies over time, then you take the integral over that, and that's how you can get the energy. Why are these important? Power is associated with data centers. And so a question you can be thinking about is, a Kansas supplier deliver the megawatts or gigawatts required? So sometimes you may have heard of data centers being close to dams because they can have that production from the water flowing through to turn turbines and create power. Another thing is associated with portable systems. How long will the battery last? So energy is more associated with portable devices. Power is more associated with data centers. So there's two primary forms of power consumption in digital circuits. The first one is switching or dynamic power, and a second is leakage power. So this is the switching or dynamic. That's when you're actually doing computational with logic gates. Leakage is the transmitters are imperfect. Even when you have your device in sleep mode or whatever, it's still leaking power, or there's things that go beyond the logic gate processing that you still have some leakage. And plus there's minor amounts of short circuit power lost during switching. And so those are things that are there. So let's talk about the energy consumed by a Cmos circuit. And the Cmos, if you don't remember, is a type of transistor that's typically used for digital circuits. So energy for a single gate change. And so this is an equation. And so that's what that would be. So what about energy consumption and clocks? And so in terms of observations and consequences for observations, energy is consumed every time there's a gate change. Many parts of a circuit run on a clock, and when the clock pulses, the input to some gate changes. So the consequence is that as energy is consumed and the clock runs, even if the circuit is not otherwise active, the rate of the clock determines the rate at which the gate uses energy. Faster the clock, more energy. So the clock change state twice per cycle. So the power used in one period is given by this equation, and the frequency of the clock is 1 over the clock cycle, which makes the power used, the average power is this equation. And I'm not going to walk through those equations. You can look in the text to read that in more detail. In terms of partial use, some systems have the ability to shut down part of its circuit, which would be really great in terms of reducing the power consumption. And so this means that there can be a variable in terms that the average power can actually be less. And so there's 3 factors that control power consumption: the fracture of the circuit that is active, the clock frequency, and the voltage in the circuit. And all 3 of those might be things that would be variable that you could modify under certain conditions based on your computing platform architecture. What about cooling and the power wall? Well, the amount of heat produced is proportional to the power used, and the power density refers to the concentration of power. All of a sudden, you're doing a lot of highly complex computations. There's going to take a lot of power. You probably noticed it when your fan on your computer starts to go on or go on higher. That would be an example of what's going on. So for chips, the power density increases as the industry decreases transistor size according to Moore's law. We talked about that a little bit. The reduction and increase of the reduction of size and the increase of number of transistors per square inch on a chip. The cooling technologies to determine how much heat can be removed. And with current technology, the limit is known as the power wall. And it's given by this equation. So for power management, you can decrease the clock rate. It reduces the switching power. It unfortunately does not help with leakage. It may mean that the device runs longer, more leakage. Decreasing the voltage has the biggest potential saving, longest battery life. So the underlying technology must be redesigned. Cell phones have already used low voltage, say between 3.8 or moving down to 2.6 volts. The problem is lower voltage increases gate delay, which means a clock rate must also be lowered. So let's talk about slower clocks and multi-core processor. Reducing the power consumption is the driving force. Consider a dual core chip where each core runs half as fast as a single core version. The slower clock rate means voltage can be lowered, reducing power consumption dramatically. So an example is slowing a clock to 1/2 the original speed permits a voltage to be lowered and cuts the power consumption by a core to approximately 15% of the original value. 2 cores running at half the clock rate consumes about 30% as much power as the original chip, yet have approximately the same computational capability. That is a wonderful trade-off in terms of saving power. So can we extend the idea to multiple cores? In theory, yes, because using multiple slow cores can save more energy than a single core. In practice, however, programmers must find a way to divide the computation among all the cores. Coordination and communication can mean that n cores cannot perform as well as one core. An arbitrary slow clock rate may not work for some applications. Say like the video, where we're used to seeing things with a video refresh rate. So what about software control of power? We can be thinking in terms of power gating or clock gating. Power gating refers to cutting power to some parts of a circuit, and it's achieved with a special low leakage power transistors. And clock gating refers to stopping the clock, setting the frequency to 0, requires software to save state and restore it when restarting the system. What about a sleep circuit? You can have a digital circuit that does this. It's common for embedded processors, series of low power modes. The software decides when to sleep and when to awake. Upon wake up, it's typically performed on demand. An example, the user presses a key. So what about choosing when to sleep? It usually employs a timeout mechanism If the circuit has been idle for a time t, then you enter into sleep mode. For user visible activities, it allows a user to specify the timeout, and for other action, it computes a break even point and then turns it off when that occurs. So what about entering into a sleep mode? The goal is to typically um, have some type of energy savings. So we enter the sleep mode only if doing so will save energy. And so we let the shutdown and the wake up times denote the times required to shut down and wake up respectively. And so we use a simplified model to analyze the sleep modes as shown below here. So what about the energy used during transitions? So we have the shutdown or restarting required energy to power back up. It's like turning on an engine, it takes some energy. And what about the energy used while running for time t or sleeping for time t? And then we have the shutting down. So startup, ambient, shutting down, those are all things that need to be considered. So notes for analysis are, this uses a simple model, and the breakpoint inequality can be expressed as a function of t and constraints. And the processors have 5 sleep modes. Model and analyze each must be extended for each of these modes. So anyway, this gives you a little bit of perspective of how to go about optimizing power consumption. And then we'll just have a summary here. And this, once again, is just a summary of these concept high-level surveys. So power is an instantaneous measure of the rate at which energy is used. Energy is a total amount of power used given over a given time. And there's 2 primary power uses in digital circuits. There are switching power and leakage power can account for 40 to 60% of the power used. Reducing the voltage reduces the power required and reduces gate delays, which requires reducing the clock speed. And there's options for software management of power, including clock gating and power gating. Many processors have low power modes, sleep modes. And because energy is required to move in and out of sleep mode, a break-even point can be calculated at which sleep mode saves energy. So thank you very much.